Hello and welcome. Today, we're diving into something we see every single day but rarely think about: light itself. We're going to learn how to get a handle on it, how to bend it, how to bounce it, and yeah, even how to trap it. By the end, you'll see how just a couple of simple rules allowed us to build everything from eyeglasses to the most powerful telescopes in the universe.
But let's kick things off with a little puzzle. We're all taught that light travels in straight lines, right? So how is it even possible that we can send a beam of light through a thin, solid, even curvy piece of glass, a fiber optic cable, without the light just spilling out the sides? It seems like it should. Keep that question in the back of your mind because we are absolutely going to solve that mystery.
All right, Section 1. Light's simple rules. To become masters of light, we've got to know the rules of the game. And lucky for us, in our day-to-day world, those rules are surprisingly simple. Okay, so technically, light is this really complex electromagnetic wave. But its wavelength is so tiny compared to stuff like mirrors and lenses that we can use a really powerful shortcut. We just pretend it travels in perfectly straight lines. We call these lines rays. So when you see a beam of light from a flashlight, you're really just seeing a massive bundle of these straight-line rays all traveling together. Simple. And these rays move fast. I mean, unbelievably fast. In the vacuum of space, light clocks in at almost 300 million meters per second. And that's not just some random big number. It's the speed limit for the entire universe. Nothing, and I mean nothing, can travel faster. It's a fundamental rule of physics.
Section 2. Bouncing light. Okay, so light travels in straight lines and is super fast. The first way we can start to control it is simply by making it bounce. We call this reflection, and it's the magic behind every single mirror you've ever looked into.
And the rule that governs all of this bouncing is just so simple, it's beautiful. The angle that a light ray hits a surface is exactly equal to the angle that it bounces off. That's it. That's the whole rule. It works for a flat pool of water, a curved funhouse mirror, a giant satellite dish, everything. Now things get really interesting when we start curving these mirrors. We've basically got two flavors. Concave mirrors, which curve inward like a cave or a bowl, are collectors. They gather up parallel rays of light and bring them all together at one single focused point. Convex mirrors do the opposite. They bulge outward and cause light rays to spread out, as if they were coming from a point behind the mirror. One gathers light, the other scatters it.
And here's the best part. None of this is guesswork. We can predict exactly where an image is going to show up using something called the mirror equation. If you know how far the object is from the mirror and you know the mirror's focal length, boom, you can calculate the exact distance to the image. It's like the mathematical cheat code for mastering reflection.
Section 3. Bending light. Okay, we've bounced light. What's next? Well, how about bending it? This is what lenses are all about. Whenever light passes from one material into another, say from the air into a piece of glass, it changes direction. We call that refraction, and it's the powerhouse behind every lens, from your eye to a camera. So, why does it bend? Well, it's because light actually travels at different speeds in different materials. You can think of it like a lawnmower going from the sidewalk onto some thick grass. One wheel hits the grass first, slows down, and that causes the whole mower to turn. A material's refractive index is just a way of measuring how much it puts the brakes on light. And Snell's law is the rulebook that lets us predict the exact angle of the bend. And hey, just like with mirrors, we've got a simple but incredibly powerful formula for this too. The thin lens formula might look familiar, and it does the exact same job as the mirror equation. It lets us calculate precisely where a lens is going to form an image. See? Bending light is just as predictable as bouncing it. Section 4. Trapping light. So, bouncing is cool. Bending is cool. But the ultimate trick is when we combine these ideas to do something that sounds, well, impossible. We're going to trap light inside a solid object. And to do that, we need to talk about a very special kind of reflection. Okay, stick with me here. It's a three-step process. First, light has to be going from a dense material, like water or glass, into a less dense one, like air. When it does that, it bends away from the perpendicular. Second, as we increase the angle that the light hits the surface, it bends more and more until it hits what's called the critical angle, and at that point, it skims right along the surface. Now for the magic. If you increase the angle just a tiny bit more, the light can't get out at all. It's trapped. It reflects perfectly back inside, as if the surface were a flawless mirror. That's total internal reflection. Now, different materials have different critical angles. For water, it's almost 49 degrees. For glass, it's a bit lower, around 41. But now, look at diamond. Its refractive index is so high that its critical angle is tiny, just over 24 degrees. This means light that gets into a diamond has a really hard time getting out. It gets trapped inside, bouncing around over and over again, and that is exactly why diamonds sparkle so much.
And that brings us right back to our mystery from the beginning. This is it. This is the secret to optical fibers. An optical fiber is just a super pure glass core surrounded by another layer of glass with a lower refractive index. You shoot light into the core at a steep angle, steeper than the critical angle, and it gets trapped. It just bounces perfectly off the inner walls, again and again and again, zipping down the fiber for miles with almost zero loss. It's a light pipe! Mystery solved!
Section 5. Building with light. So now that we know the rules for bouncing and bending and even trapping light, what can we build? Let's see how these simple rules are combined to create tools that give us a kind of supervision, letting us see far beyond what our eyes can do on their own.
Let's start small with the microscope. It's basically a two-step trick using two lenses. The first lens, the objective, has a very short focal length, and it sits right up close to whatever tiny thing you're looking at. It creates a first image that's already magnified and real, meaning you could project it on a screen. Then, the eyepiece you look through just acts like a simple magnifying glass to blow up that image even bigger.
Now let's swing to the other extreme with a telescope. It also uses two lenses, but the objective lens is totally different. Its job is to see faint things that are incredibly far away. So it has a really long focal length and a big, wide opening. Its main purpose isn't really to magnify, but to be a giant light bucket, to gather as much faint light as it possibly can and focus it into a small, bright image. Then, just like the microscope, the eyepiece magnifies that little bright image for you.
So if you put them side by side, here's the one thing to remember. The microscope's objective has a short focal length to make a big image of something tiny and close. The telescope's objective has a long focal length to make a small but bright image of something huge but far away. It all comes down to what that first lens is designed to do. But what's really interesting is that the biggest, most powerful telescopes today, they've actually ditched the objective lens entirely. They use a giant concave mirror instead. There are a couple big reasons, but one is that mirrors don't suffer from something called chromatic aberration. That's when a lens accidentally splits light into a slight rainbow, making the image a little fuzzy around the edges. A mirror reflects all colors at the exact same angle, so the image stays perfectly sharp.
So let's just step back and think about that. We started with two incredibly simple ideas: light bounces and light bends. That's pretty much it. And from those basic rules, we figured out how to build instruments that let us see the tiny cells in our own bodies and the most distant galaxies at the edge of the known universe. That's pretty amazing.
That whole journey, from somebody noticing their reflection in a still pond to building the Hubble Space Telescope, was all about mastering light. It completely changed our place in the cosmos. And it really makes you wonder, right? What fundamental force of nature are we just starting to get a handle on today that our descendants will master to give us our next super sense tomorrow?